All right, today's lecture shouldn't be too long.
Yeah.
So we can watch the rest of the movie. So today we start double and triple integral 3. So now we're going to do triple integrals. So what we're going to do now is we're going to add up an infinitely small cubes like this. So of course dx, dy, dz. So you're just going to take the volume of that thing. Of course the order doesn't have to be this. And then you just add them all up over what we call t. See, in 2 dimensions we call that region omega. In 3 dimensions we call it t. Okay, so let's do a couple examples. Let's do a simple one then. How about, so in the xy plane, let's say it's the region bounded by, lose money, y equal x squared, and how's about something like this? Y equal 2x. So what are the intersection points? 0, 0, and 0, 2, 4, yeah? Just by inspection. Okay, so this is like the omega region, and then it's bounded above by something. What shall we do? Anybody? Okay. Z equals x squared plus y squared. So that's like a parabola coming up like this. Okay? So find the volume of the region where this is the base and then bounded on the top by this parabola. So I would probably say you want to go dz first. And then how about dy and dx? And again, the last one has to be constant, otherwise you can't compute it. So z is going to go from, again, from low to high, right? So what is this? Z equals 0, that's the xy plane, to x squared plus y squared. Okay, now we look at this region over here. So if you integrate it with y with respect to y first, then you're going to go from the bottom to the top one. What's the equation of the bottom curve? From x squared to, and what's the equation of the top curve? 2x. And then the last one, if you integrate with respect to x, 0 to 2. Now, is this integral easy to do? Yeah. Well, let's just try it for funsies and see what happens. So what's the integral of 1 dz? Z, and then you have to go from 0 to x squared plus y squared. So you get x squared plus y squared minus 0. Now you have to integrate this with respect to y, and then you got to go from x squared to 2x. Okay, so integrate with respect to y. X squared y plus 1/3 y cubed from x squared to 2x. Yeah, this one's not going to be that difficult. So plug in the top thingy. Plug in 2x there. 2x cubed plus, plug in 2x there. 8/3 x cubed minus, plug in x squared. Hey, this looks like one of the problems from the homework. Plus, plug in x squared there. 1/3 x to the 6. And then now we got to integrate this with respect to x from 0 to 2. So can we simplify that? Yeah, we can simplify this a little before we compute it. So what is this plus this? 14/3 x cubed minus x to the 4 minus 1/3 x to the 6 dx. Antiderivative? That's gonna call in people. Song, and the derivative?
14x to the 4th over 12, 7x to the 4th.
Say that again. Okay, come on, let's reduce our fractions here.
7x to the 4th over 6. No. What? Oh yeah, 7x to the
7
4th.
over 6 x to the 4.
Minus x to the 4th over 5.
Uh-huh.
Minus x to the 7 over 21.
Okay. From 0 to 2. So if you plug in 2, here, I'll just leave it like this then. 7 6 times 16 minus 1/5 times 32 minus 128 over 21 minus 0. And then, of course, you got to simplify that for 1 point, yeah? Make a least common denominator of
630.
42 times 5. 210 then would be the least common denominator, I guess. Okay, that's an easy one. Let's look at a more difficult one. So you guys understand the concept though, right? So instead of adding up an infinite number of French fries, whatever, dx, dy times z, we're just adding up an infinite number of infinitesimally small cubes. Okay, so let's say we have a graph on the bottom, which is z equals square root of x squared plus y squared. Learner, what is that? This is a quadric surface that we learned, and you guys got A's on. Quadric cone, except just the upper half, right? Because it's positive square root. So it's kind of like this. Keeps on going forever, yeah? And then it's bounded on the top by, let's make it an ice cream or shave ice or something. What could be an equation of that to cap off the top? Just like a sphere then? Okay, what would be an equation of a sphere then? Because here's the origin. Come on, give me an equation of a sphere. Look, you just go x squared plus y squared plus z squared equals, what do you want the radius to be? You want a small, medium, or large ice cream cone?
Medium.
Okay, then give me a number. Equal.
4.
That's small!
60.
Okay, that's better. Okay, so if you solve for z squared equals 16 minus x squared minus y squared. If you want the upper half only, so z equals square root of 16 minus, why don't we just go x squared plus y squared. Okay, so let's write a triple integral that will represent the volume of this ice cream cone here. Okay, so root, root, root. Probably we'll want to go z, y, and x. That's the typical order there. Okay, so z is going to go from the bottom curve to the upper curve. That's easy, yeah? So what? This one to that one, right? So square root of x squared plus y squared to square root of 16 minus x squared plus y squared. Okay, now what about y? Now how do you figure out the limits for x and y? What are you going to do? Well, do you see, like, okay, whatever this three-dimensional thing is, if you look down from above, from the heavens onto the thing, you see the projection of this onto the xy plane. So if you smash this down onto the xy plane, what are you going to see? Aren't you going to just see the circle right there? So that's how that's going to be like your omega. So smash it down onto the xy plane, you're going to see the circle. So how do I figure out what that circle is? You got to find where they intersect. So what's the best policy here? Yeah, so substitution. So z equals this, so z squared, we can substitute it in there, right? So x squared plus y squared plus z squared, which is x squared plus y squared, equals 16. So you got x squared plus y squared equal 8. Did I do that correctly? So that means if you look down onto the xy plane, you're going to see a circle of radius 2 root 2. Okay? So here's the equation of the circle. So how do you figure out the limits of integration for y? You're going to go from the bottom curve to the top curve. What's the equation of this bottom curve? Well, if you solve for y here, you're going to get y squared equals 8 minus x squared. So y equals plus or minus the square root of 8 minus x squared. So the bottom curve is, of course, the minus one, and the top curve is the plus one, right? So it's going to go from negative root 8 minus x squared to root 8 minus x squared. Of course, you have symmetry, so you can just go 0 to that and times it by 2, right?
Yes.
Wait. Let me think about that. Can you do that? No, yeah, you can, because we have symmetry. And then what would your limits for x be? Well, x is going to go from here to there. So wouldn't it be negative 2 root 2 to 2 root 2? And again, you have symmetry, so you could have gone 0 to 2 root 2 and times it by 2 then. Got to make sure you have the symmetry though. So you understand how to set up the integral? Okay, now, is this integral difficult to do? Well, let's try it for funsies. So what's the antiderivative of 1 dz? Z, and then we gotta go from root x squared. We're just trying this out to see if it's gonna work. Okay, plug in the top thingy. Plug in the bottom thingy. And now we gotta integrate this with respect to y from negative root 8 minus x squared to root 8 minus x squared. Can you see that this is going to be a mess? Because how do you do this one if you're going to integrate with respect to y? In fact, both of them you got to do a trig substitution, right? That's crazy. And then you got to plug these things in after you find the integral. It's going to be a mess. So we're not going to learn it now because today we're doing rectangular, but because the next time, tomorrow, we're going to learn about centroids. So it's going to be the next time. Maybe this one would be better to integrate in terms of either cylindrical or spherical coordinates then, right? In fact, whenever you see the quantity x squared plus y squared, that's kind of like a hint that you should do it in cylindrical. In fact, why don't we just do it for funsies, because you guys are smart enough, right? So instead of going dz, dy, dx, we can go dz, and then remember, we just finished cylindrical. R, dr, d theta. So z would go from the same thing, except what is this? R. And what is that? Root 16 minus r squared. That's going to be a little bit better. You still might have to do a trig substitution though. And then what about r? Okay, here's our omega region. Smash it down onto the xy plane. R is going to go from 0 to 2 root 2. And then theta is going to go 0 to 2 pi. And you get the same thing, but this integral is going to be much easier to solve. But see, when we get to the test, what is the test, by the way? And notice I put it on extended, you know why? Because there's a lot of integrals to solve. So we need that extended. All right, so we're done with that. You just got to practice. Actually, I finished the videos for this chapter this weekend. I thought there was a secant to the fifth.